Esta es, hoy tenemos al doctor Simon Kemp. Los errores siempre ocurren, los problemas siempre pasan. Compartimos pláticas acerca de observing also this brightness futures of galaxies.
Okay. Okay, thank you very much. I was just saying here yesterday I had some technical problems with not having electricity or internet. So it's not quite the talk I was planning to give, but I think it's got about 90% of what I put on the abstract in some form or another. I had to compile it from existing talks, so I couldn't download anything new. This is my main area of research. First, for those who haven't been to the Institute of Astronomy or Institute of Astronomy, has anyone not been? Yes, this is an area of the area around the Institute in Guadalajara. For those who are maybe not on YouTube, not in Guadalajara, the Arcos and the buildings of the IAM here, including the gardens and the old telescope tower, which is the Doppler radar. Now, this was what it looked like in about from the 1940s, when it really was the entrance to the city. So the IAM building was there at the time. It was built in about 1942, I think. Gardens of the Institute often can sometimes be full of thousands of people when there's eclipse. All the public come and use little telescopes to progress. And this is part of the observatory of San Pedro Martir in Baja California, the main optical observatory in Mexico. Although these aren't the old telescopes, they're part of a collaboration with Taiwan, I think. It's a Picacho del Diablo, highest point there. My areas of research, well, we're going to be talking about some things on the first four today: structure and morphology of galaxies, interactions of galaxies, groups and clusters of galaxies, measured by photometry, measuring the light, and spectroscopy, measuring the spectrum. Some other areas mentioned there. I put this together from various other talks yesterday. I do have some slides in Spanish, but I'll translate them. Now, a galaxy has 1 followed by 11 zeros, which is normally 100,000 million, is it? 100,000 million stars, 10 to the 11, or 10 billion, no, 100 billion if you're using the 10 to the 9. The forms ellipticals, spirals, lenticulars, or irregulars. They can exist alone in field galaxies. Galaxies by themselves are very common, or interacting with other galaxies. Binaries, groups, clusters, where it can have thousands of galaxies. And many of them, they're very bright, they're also at large distances, and so they are actually very diffuse, very not concentrated, very faint light. Basically the faintest objects commonly observed by astronomers. And the night sky without contamination is very dark. It can appear very light as well once your eyes are accustomed to the darkness out in the out in the fields, the countryside, but only the central part of galaxies are brighter than the sky itself. And this is the real dark sky, not the contaminated sky. And we observe galaxies, when I say low surface brightness, faint until 1% of the brightness of the sky, which can take many hours of exposing the camera to have that sensitivity. Typically, we combine many images for a total exposure of many hours when we're observing galaxies with telescopes of 1 to 2 meters, which is what we have in San Pedro Marte. Scale of telescope. You can see probably, but we imagine a galaxy with a bar and the spiral arms. Covering it all in the center here, maybe we're a bit brighter than the sky itself only. We want to follow it out here to the faint bits of the arms. We can be just 100 times fainter than the sky. It doesn't need many hours of exposure. Hubble tuning fork, not a very good resolution slide, but here are the ellipticals, the different, just classified as going more from round to more elliptical. So we only classify in 2 dimensions. These are the spirals, which start very concentrated and there's longer arms on this end. And these are the ones with the bar in the middle. And the arms, and these are in between objects, lenticulars, which are like lentils or lenses of the form. They have discs but not spiral arms. In the history of astronomy, in finding objects to which to find faint features, catalogues have been very important. This is the most famous, smallest, but the longest, 200 years ago, a Frenchman who wanted to find comets, and he kept being annoyed by seeing nebulas or faint galaxies or clusters of stars which never moved, so they weren't comets. So he made a list of them, of non-comets. It's quite a useful catalogue with the Pleiades and the Ring Nebula and Andromeda Galaxy, many globular clusters, and quite a few galaxies as well, some of which we'll see in a moment. And there's bigger catalogues, NGC, but they start lists of objects to find something interesting, to observe in more detail and try and find something interesting. The faint features of galaxies, we're going to be seeing examples of all these types. Faint extended halos, the galaxy which just goes on, the halo or envelope around it. The interacting galaxies are filaments, tails, or bridges between them. Tidal features. And the diffuse intergalactic medium is just like the interstellar medium, but between galaxies. Between galaxies in a cluster, we can find faint light. And low surface brightness galaxies, simply galaxies which never formed many stars, and so they aren't particularly bright. They're quite difficult to detect. So this is one area I haven't particularly done much work on. Still part of my interest. Schmidt plates were important for detecting faint bits of galaxies as well. The Schmidt telescope isn't the type of optics, it isn't particularly big, 1 meter or 1.5 meters of mirror, but it has a very large field of view, which is about 5 degrees by 5 degrees. Looking at the full moon or sun is half a degree, or 5 degrees if you imagine the Ursa Major or so, which was sort of star. 5 degrees is about the separation between any pair of stars, those pairs of that. So it's sort of, but a much bigger field of view than a conventional telescope and camera, which means you can even do the whole sky, though it takes about 400 fields, but it's factorable. And you can take long exposures, and this is one of my projects, which we did many years ago, but we're still finding in lots of the faint spots of galaxies, and still can find faint features around them. It's one of the deepest images taken. It's not a Hubble deep field, but it is 13 hours on the telescope in total, combining 13 1-hour exposures, and this was but still with photographic film, so it will be scanning all the images and co-adding them digitally. This is part of the Virgo cluster, which has some of the objects in this area here. That's M86, M84, M87, M89. I think one of these is M49 as well. But this is the actual center of the cluster, and you can see there's some faint light more concentrated around here in optical. Note we like using negative images in general for this. Obviously, the black is the brightest, which is what happens on the original photographic plate or film. The photons arrive and make it darker, make the emulsion darker, but it is actually easier on the eye to see the faint stuff against a lighter background than a darker background than in white against a black background. These are all giant ellipticals here. There's a bit of a jet. This is one of the famous ones for having the what we call event horizon telescope, combining various radio telescopes to take an image of the black hole in the center. It isn't seen here. That's for the scale. If we follow this to its large halo here, it would still be big. It is actually bigger than the full moon in terms of being nearly a degree in size. Take a look, contour on that. This comes from my first paper, my doctorate, and they are both image statistical design here. It's supposed to be the same field, so that is the center of that. It's just effectively different contrasts, changing the black and white on the digital. That is fairly far. This is a large galaxy in itself, but its halo extends sort of more than 10 times as much as the giant elliptical central regions. And you can see a couple of objects here which clearly aren't stars. No, a lot of the very round ones are stars, more point-like, a bit more diffuse, and galaxies, and it's the center of that. The center of a cluster of galaxies, a large CD of galaxies, these are called. For no readily apparent reason. See, it doesn't mean, people have said it means central dominant, but it wasn't the original idea in the cluster. A D galaxy is a giant radio galaxy, and the C in front makes it with a diffuse halo. The letters as such don't mean it. Some of my recent projects, I don't tend to go for the trendy ideas. I go for galaxies that interest me in general. And one of my side projects is a lot of these deep imaging started in fact in the 1970s, 70s and 80s, before we started with the photographic plate, before we had electronic cameras, which mainly have smaller fields. And so they did publish some things which, when you look at them now, seem a bit dubious, no, whether they exist or not. So sometimes I have re-observe some old detections to see if they're correct or not, because you can have lots of reflections of contamination in the light. This was a similar object to the one in my first paper, but its halo seems to have a sort of funny shape down there and not take the natural elliptical form that relaxed objects normally do. But we did some electronic camera images so recently in San Pedro, and we found that there is this shape. See, does seem to exist. It leads to the bright star here, but its star is closer, of course. This galaxy has never been the easiest to study, but it does have lots of bright stars in our galaxy, quite close to it. Difficult to take out completely. These end up a bit of greatest hits now. This is one way we're expecting some data soon. A is for Abel. It's a cluster. A catalogue of clusters of galaxies, not a cluster of catalog. Catalogue of clusters of galaxies. This one has one of the biggest halos reported. Doesn't look very impressive in its field because it's a few times further away than most of the galaxies we've studied. And in these cameras, although you hear many studies about galaxies at high redshift 9, 10 or so, new galaxies being formed. In fact, this is only at 0.15 or 0.14. still quite far for me. Typically, note that in many of these, our galaxies just about, I observe galaxies just about at the distance where they fill the fields of view we have. But one needs 2 fields to fit it all in. This getting towards the blob. They don't have to be very far away because before they really do it just into points in observing from the Earth, and that's why you need telescopes like Hubble Space Telescope or James Webb Telescope to resolve the detail in the points, not to resolve the details in the blobs. See distant galaxies. This one is of interest. It was published and reported a very big halo, about 10 times bigger than normal, including some of the big ones we've seen here today. I did ask one of the people working on it at the time, and he said, yes, we thought the data was fine. A couple of years ago, we got a proposal accepted to take deep images of this with a very large field of view, to really look for the main problem is that the halo is as big as they said. As the publications, INLA said it would be many fields across in this type of camera. So we got time on a telescope, which has sort of a degree, fields of a degree across, and they took some deep images with it. Trouble with those is that they're also very, very big to process on normal computers. But at the observatory, they have been processing them for us. See what the combined image looks like shortly. The project with Gerardo Ramos and Alberto Nicochi. That's the idea. These galaxies have the normal halo log radius. And this is brightness. Remember, in astronomy, magnitudes, smaller magnitudes are brighter. So here we have 16, here we have 30. So the galaxy goes down in brightness, and that will be the normal fit, but it has all this extended fit. 3 years, as we see here. Log 3 is a thousand kiloparsecs, 1 megaparsec. Quite far. Okay, interacting galaxies. This is sort of the part of the Hubble catalog, which shows you all the configurations of interacting galaxies. Basically, it's that one galaxy perfectly happy on its own. If it has a disk, or the star, if it's an elliptical, the stars move in every direction. If it's and we express the distribution of velocities with the sigma of the distribution. If it's a disk, it's rotating, mostly at the same velocity with radius for most of the radius of the galaxy, and because of the dark matter, usually with a typical velocity of rotation. But the rotation of the disk tends to get disrupted when there's an interaction, because there's a huge great addition to the gravitational field just arrived now, and deviating all the stars from their orbits. So the gravitational interaction tends to end up with an elliptical at the end. One of the ways to form ellipticals, so they do form at the beginning of the universe as well. But the interaction between galaxies can also start with 2 spirals. You can end up with 1 elliptical with the stars moving in every direction. And the filaments that form sometimes can be due to a group of stars orbiting together, and all are deviated from their rotational route, but they stick together, and so they might form a filament further out. Carry on. And some of our best galaxies was observed in terms of interactions. I should really have other images of this to compare it with, so you can see what's going on with the NGC 4410, but there are two galaxies here already interacting. There's a third there and a fourth there. They're all connected with filaments. They all have, and there's a sort of arc here as well. So maybe in what will it be? A billion years, if we come back, this will just be one elliptical formed of the remains of all 4 of the galaxies. This is from the 13-hour exposure. This is another one. It's spot the feature. It's this that will interesting. This galaxy seems to have a little tail. This is really one at the edge of visibility, including here, where you can doubt or not whether it exists, whether it carries around there. This is one of my favorite answers to a referee's report that I was able to give, because I don't have the image here, but this galaxy had been observed with Hubble, and they found a small but bright satellite galaxy passing as if in front of it. The referee pointed out to us in the paper. In fact, I think I had seen the paper before, but it was 100 pages long, and a few years ago, downloading 100 pages with the internet connections didn't always work. But I think I read it. But there was a bright spot in front of the galaxy, but the referee said reasonably, it won't be visible in your data because you don't have the resolution and it's hidden in the brightness. I was able to point out in one of the images, I think it was already in the paper, that we did have it. There it is. And the reason is that this is one of the techniques I mentioned in the abstract. Residual image is making a model of the galaxy with contours, isotopes, elliptical symmetry. Make the model image and subtract it from the original image. And then you'll be removing the main body of the galaxy, but anything which doesn't have elliptical symmetry will remain in the image. And this is what happens here. And this point, this galaxy didn't have it, it's just a point, of course, and this will be crop the scale out in this artistic display here, but I think it's something like 5 arc seconds from the center, and that corresponds to 5 arc seconds from the center and the south. And note we also see modeling it as an ellipse doesn't take into account that there's a disk hidden in the galaxy, which is exactly east-west. These parts here are the hidden disk inside the galaxy. Most galaxies we saw the Hubble tuning fork, on the Hubble, and basically all galaxies are some combination of a bulge component, which is the center of spirals, or on elliptical is all bulge, and a disk component. Spirals have disks, but some ellipticals have hidden disks as well, and all galaxies are combinations of the two, although the proportion can be 100% to 0% in some, but not so many in the end, and that's a hidden disk in the galaxy. Disks also seem to have brighter light on the 90 degrees as well, so they're indicated by a cross in these diagrams. And these are just foreground stars, probably, or maybe other satellite galaxies. It was definitely the brightest. And the idea of this satellite galaxy is making a pass through the central regions of this galaxy, and this is basically mapping out its orbit, where it's been taking stars with it or leaving stars behind. And this was another image of this galaxy, and I forget whether this is the new or the next generation Virgo survey, but it does mean sort of the same thing. Although I can't find a publication of that, it only seems to be in a talk I found online. But follow the curve there, it's actually a bit brighter on this. It's not probably doesn't go across too far. Yeah, we also must find some concentrations in this that aren't stars, they're too wide. Wide profile, which are probably tidal dwarf galaxies. We call them in formation. Coming out of there. This isn't as a normal interacting galaxy. This galaxy here is passing it too fast. The difference in the Doppler radial velocities are about 600 kilometers a second, which is too fast really to have any interaction between the two. Now we get on to some of the things that we're doing now. The little time I have for research, this is what I'm at least trying to do. This is another image from that field, although I think this is an electronic camera. The problem with this galaxy is, what is it? Because, well, first it looked like a bar, sort of this thing here could be most of that. And it does have 2 spiral arms, but they barely start. Although we cut it off a bit here, they don't really go much further than the edge of the field. So it could be a spiral galaxy, maybe with one of what we call fossil spirals, which have There's not much more star formation now, so they're not, the arms aren't very bright. But the disk, is there a disk? Not really. In that case, it's just a bar, really, with a bit of arm. Could it also be an edge-on galaxy? There are some, I said, but not fits the bar. This is face-on, as we call it, friendly. Edge-on, the canto, if we're looking, this is the plane of the disk. These then becomes a warp, like an integral sign, no? But it's really gravitational instability. Some galaxies do have a disk which curves up at one side and down on the other, like a sort of warp, like the old, well, not old now, they're coming back. The vinyl records, city. And if it is, it's one of the most warped known, but there are ones warped to that degree. Or it could just be an interaction as well, and these are more tails, tidal tails, not arms. And there's three possibilities. So the galaxy isn't particularly bright. I mean, luminosity, nothing. So it would need two small galaxies to form one, not quite so small. So there's the three possibilities. The residual image here as well. Although here, we're obviously modeling something which isn't very elliptical, so it won't work quite as well. Probably not an elliptical hit here, but apparently this X shape in brightness here is a characteristic of a bar. I suppose a bar would have, you have the bar there, the bar is quite rectangular, so if you imagine an ellipse, it does have more light in the four corners. That's why there would be more light in the four corners. That would suggest the bar explanation is correct. We also use another technique I put in the abstract was the color map. This is calibrate an image in one filter, calibrate an image in the other. So the pixels really are the magnitudes. And if we subtract them, we get and we can put a scale of the rainbow on it to get an idea of at least of which stars are more red, which stars are more blue. As these are sky subtracted images in these, and we subtract 0 by 0 then, so the color of the background usually doesn't make much sense because it's 0 and infinities. But here you can see the bar is very red, which stars, and the arms, although it's getting noisy, do look a bit more towards the blue side. So it is noisy, although which would mean that it can still be a bar, but they're not quite as fossil as we thought. If they still have some blue colors and some star formation, maybe. Both those seem to favor the spiral. We also have, I don't quite have this ready to put a slide on, but we did. One way of distinguishing what happens here is if it's edge on, it should be rotating in the line of vision. This side maybe is going into the screen, this side is coming out. So we should be able to see the difference in the velocity for the Doppler effect. One side to another. We tried it, and there's sort of a difference of maybe 60 kilometers a second, which isn't very much, not really a rotational speed. It's a bit on the edge. We need more resolution, really, but that does seem to imply that there's not much rotation. So if it's not rotating, it's just more likely to be a face-on galaxy, and that this is a bar. But stay tuned for this. That time to write the paper. It'll be very long. Okay, and this was a bit. Now we're going on to faint emission in clusters. We've already seen the Virgo cluster with a bit more light around the biggest galaxies, and this here, so to have a bit more light in this area as well as this galaxy, which has some sort of filaments coming from it. Okay, for most of the rest of the talk, I'm going to be talking about Stephan's Quintet, something we're working on a lot now. It's quite a famous group of galaxies. It comes up with the pretty pictures a lot, although we're actually looking more at the area of it than the quintet itself. It's called a quintet because there are 5 galaxies. Which ones they are has often been the matter of debate. It's changed a bit over time. It does have clearly interacting galaxies, so 7318 becomes an A and B because it's really two, and 7319 is a bit irregular. 7320 turns out it's much closer to us than the rest, about 7 times closer. So if we go in this direction, we meet this, and then 6 times more distance we find the others. Basically, even then there are some. Although it appears the biggest galaxy, it's a bit bigger because it's closer. That's not really part of it. There's an elliptical here, and apparently this galaxy is at about the same distance as well. So the 5 of the quintet turn out to be 1, 2, 3, 4, 5. It's indicated here with that velocities now from the recession velocity for the Doppler effect. The close one is at 787 kilometers a second, quite close. The others are around the 5,000 and 6,000. So there's 3 about 6,7, 6,6, 6,8. There's 2 at 5,8 and 5,6, including the one a bit to the side. But the general, this show the tails? Not really. There are some filaments that come out here where it says tidal tail, but it's not visible here. But studies of this group have indicated a complex history in which this once passed through the group, which has a high relative velocity to it. So it ends up on the other side, but it formed some of the tidal tails and the interactions. Well, this shows some of that. Some of the work of now in astronomy, it's very important all the different wave bands, and often we can just download images in different wave bands, different wavelengths from the repositories of data, including some telescopes which you have to compete for time. Often you only have a year with the data, and then it becomes public for everyone to use. The main problem now is that there is too much data out there. Too much data out there, not enough astronomers to process it all. And so they still work on the objects that everybody does, like Stephan's Quintet. This is an infrared image from a satellite. Not all the only a little bit of the infrared light passes through the atmosphere and shows regions of star formation in the galaxies and dusty regions. The galaxies and X-ray Chandra, which were named after Chandrasekhar, people who are in about the 1930s identifying the nucleosynthesis method of generating energy in stars. And this shows that there's sort of a huge shock front here between different interacting parts between the galaxies as well. So often you need all the different wave bands to put together all the information of a galaxy. This looks a bit less interesting, but here is Stephan's Quintet. And the field of study also includes another galaxy, NGC 7331, which you can probably tell is quite a big one, but also a lot closer than Stephan's Quintet. So it is apparently at the same distance as this one, the one that's not really part of the quintet. So those two may be related, separated by a bit, which is part of the story I'm going to say about these now. You may just notice, so it's not so prominent in this, but some parts of the field look a bit dirty. In fact, these seem to be gas filaments. And Arp is one of the famous astronomers for being one of the mad ones. He was the one who never really believed in the redshifts of the galaxies and thought there was some other physical process than the Doppler effect, because he found objects which seem to be connected, although they're vastly different redshifts. Like these, for example. And some of those do look quite strange, but I think the statistics of it all suggest that they're just chance alignments of objects. No, we always have the problem in astronomy that we're observing in a sort of cone in every image. No, so we see stars in our galaxy and other objects in our galaxy. Then we may arrive at a nearby galaxy, and then there may be some dots in the image which are galaxies really far away as well. But they all don't come labeled and how far away they are. So it's work to work out which are the close objects and which are the far away ones. Obviously, we can say by size, but not always. This and the rest. There appear to be some filaments between them, which may be connected with the galaxies, or they may filaments between them, which may be connected with the galaxies, or they may also be in our galaxy. Cirrus clouds in the Milky Way. Let's see. ARP returned, but this seems a, well, though this seems a more sensible project for ARP, he was really interested in whether objects with different redshifts really were at different distances or the same distance, or similar distances, and if they were connected, and if there was a connection between all these groups as well. A few years later, he got a few years later, he got a deeper image, not a later. It's obviously a later. It's quite confusing, but there's obviously quite a lot of filamentary or diffuse material in all the field. Now, this is Stephan's Quintet down here, 7331. So did a study in some detail of these. It's on the laptop and on the screen. You can see a bit more. Yeah. Some of these are visible in the wide satellite at 12 microns, which is, well, 12 microns is basically around 250, 300 Kelvin is what we're all emitting now. So general mid-infrared radiation or heat. So it's quite difficult to observe these from the Earth because everything is emitting that. So it's from the satellite at 12 microns. If we look, there's the Quintet, there's 7331. This is a rather strange object which isn't visible in the visible, it's visible in the infrared. I don't know exactly what that is, but some of the filamentary structure seems here as well. So it's quite possible in those that the filaments just are in the Milky Way, and it's just some warm gas, warm dust in them sort of being heated here. So what's here and here seem to correspond to what's here and here. No? That's another coincidence. So a lot of this may not even be connected with the galaxies. So I thought it would be interesting too, this is part of my type of projects of revisiting old observations to see if they're real or not, if they're detections in the 70s and 80s. I mean, this looks more real and not reflections or anything, but interesting to work out what they are. This is ARP's catalogue, so we're going to go through the filaments in a moment in alphabetical order to see where they are. A, B, C. I've never been that convinced with C. D, a ring. E and F seem to come out of the Quintet, so they're the ones most interesting from the extragalactic view. G is well known as a tidal tail in the Quintet, and there's a H here which looks more like an N. So some of these are quite convincing. Some of these are okay. Where's that in the? Which one is ARP seeing today? E and F are some of the strangest, but because of the original evidence from these, I thought, nah, they don't exist. I'm not sure if you're convinced by two lines coming out here. One, two there. They are visible, but not very straight and very sort of distortion. This is the same field again. A and B are quite visible here. That's D, and C is some of this. It's the tidal tail in the Stephan's Quintet. One was well known anyway, and ARP added another. But these two coming out, yeah, maybe two lines are visible there, but this is what we do in faint features of galaxies. Of course, we observe things that we're not sure exist. So I started a project to observe some bits of this. Our CCD field in San Pedro Marques only covers sort of, maybe we'll cover the Quintet just about in one, so we can only do bits at a time to detect them. And there is a student working on this from here in modular projects a few years ago. We did some observations. 2017, 2018 dawns. What do I find? This gets published in one of the main journals, which were quite popular at the time, and probably still is, although it's effectively taken for a calendar on a semi-cloudy night. Not real, not particularly for science. Canada, France, Hawaii telescope. Hawaii, I think, 6-meter telescope. It's a big field of view, so they do it all. This is basically the same field, slightly wider than Arp and Laurie did. NGC 7331, Stephan's Quintet, filaments A and B. I think that's part of A, but then I don't see B if I do that. I'm not sure. One of the strange thing here is that Arp never catalogued these, and they seem to be brighter filaments than some of the ones he did. This field goes a bit further over, but
These picture colors are because of the materials of the stars.
this is it was done in 3 filters. So with 3 filters, you can do the red RGB, red, green, blue technique. So assign a color to each one, and then you have a sort of false color image that's representative. I'm not quite sure if there are so many blue stars here, because blue stars are always not so common. There seem to be a lot in this field, so I'm not quite sure it's right that they should be so blue. But the stars of the galaxies generally are red, I know. Apart from where there's star formation, the galaxies do appear sort of orange or yellow-orange at least. Yeah, it's a false color. And I thought, hecho mi proyecto. No, I should say that in English, shouldn't I? What's it in English? I thought they'd done the bloody project. But I did meet the next year at a conference. And said we were doing some things on this too, and he was very nice and gave us his data. Because as I said, the project wasn't really image wasn't really taken for scientific purposes. It was more to create a pretty image on a cloudy night. No? So they weren't really working on the filaments, so we got that data again. And here, well, and we see E and F. No, I don't see anything there. There's the N, which is the what H. No? So we have the data, and the master's student has been working on this for a few years, and we're just about ready to submit the thesis. Basically, we tried to collect all the information on every filament. Look at this, as though we have the 3 images. Gerardo Ramos as well has done his own false color, because we got the images. Gerardo Ramos has done his own false color version of this as well, which is probably a bit better. We don't know if we can publish that, because it's very close to the original. We'll see what we do when we write the paper on this. We've basically done all the figures now, and the student has been looking at the data sets on the internet as well to get to see, and I said the Y is the infrared data or the ultraviolet satellite, or if anything in the radio exists for this field. And what could these be? All these filaments? Well, it could be interactions between galaxies. Those galaxies aren't very clear. Some of them could be radio filaments. These are radio filaments, the center of the Milky Way. Sagittarius A is where the black hole is at the center of the Milky Way, but it doesn't seem obvious that they're radio galaxies here. There are some radio sources in the field, which I'll mention in a minute. It could be radio jets or filaments, I say, or most probable for most of them is they're just what we call galactic cirrus clouds, like cirrus in the atmosphere. No, you see, it's the cloud that's a bit more stringy and filamentary. They exist in the galaxy as well. Milky Way, I mean. Well, now we'll go through all the filaments in order. I have put another copy of this for. But we start with A and B, which are here, sort of parallel but separating. C is like a long tail of this galaxy. It's interesting. D is a loop near that. They all seem to exist. A is here, and the Pierre Alain Duc is the astronomer who took the image from Canada, France, Hawaii telescope. Although here I do have some copies of these in negative, which are easier to see the filament, in fact. But that's it for my cut in electricity yesterday. I wasn't able to use the internet to get that. Filament A runs through here. Very dense field with stars as well. I find this region as well, although it's not actually in the plane of the Milky Way, it's about 20 degrees above. So it seems a little overdense to me. But to quantify that. Filament A, this was observed in San Pedro Martir. This is infrared, and we see the infrared basically as the emission, the same area and shape as the filament. R is the red band in the optical disc. And here it is again. Here is Galax. You can say Galax or Galax, but that's an ultraviolet satellite telescope. And although it's very noisy, we can sort of see a bit more noise where the filament is. There's more white points here in this part, so it seems to have some ultraviolet emission as well. It does rather suspect that there is some ionized lines, nebulosity in the region. Although not clear if there are any stars doing it or not, but that galactic cirrus may have that feature. And this is another sort of red, green, blue done by the student in this, in which his images all seem to turn out green. So yeah, it's just the three colors and the optical doing a marking out where the filament is there, and go all the way. And here, filament B. This comes out quite well here, but it exists. You can tell that I spend all my time with faint objects, so I call that quite well, but there is something there. Filament B in the Duke R band. This is where some of the radio sources are that I mentioned, which is what drew up to this field, in fact. Radio sources are in the red point, so I think that one is actually wrong. It should be more down here, but the ones up here are right. And there's the filament A. This is a negative, so you see it sort of does look more convincing, the form of the filaments in negative, the high contrast. And there's A, and there's a source here, and there's a source here. Are they connected? They're aligned. That's something. Alignment, whether it could actually be a, but of course, this is optical emission, not as far as I know, seen in the radio, and these are point sources that emit in the radio. So, but there are jets in the radio that are seen in the optical, so like the M87 one, the galaxy went through. So, is it a connection? It's a hint of a connection. That's all we can really say about that. And the other one is actually on the ring diode. I think this part here. This has now been replaced by another diagram with a wider field. Show the location of the other. Oh, that is Spanish. AB filaments, radio sources of R. Filament C. I'm not convinced in this, but there are nebulous diffuse bits coming from the end of the galaxy and maybe carrying on down here. That's not my most convincing. Filament C. Sorry. This is another diagram which is probably slightly more accurate than the one ARP did, what they really are. D and D, although D should be more oval, that's the point on it. It looks like he's not drawing ovals, so it's all one there. That's E and F coming out. Yeah. Well, another one with filament C. Can I see it there? Here. I get confused by the spectra and that's at the top of the image. So there was a H2 region around the stars, which is sort of a shell of ionized gas around young stars. Just part of the filament. D. You're probably not going to believe this one, are you? It's not the best image. I have seen more convincing ones, but this sort of does seem to be a loop here. There's that of there. There's a ring there. Another RGB. We have more convincing images. E and F, do they exist? Well, I was a bit surprised when I looked closely at the images of Duke. Yes, they seem to do. There's one there and one there. Are they convincing? 50%, but they're in the same place as where the lines are on the ARP image. So it's another independent image. This seems to be, and this is the direction to 7331. I think a referee in a conference proceeding wanted to show where 7331 was. These are in the direction of the other galaxy, which is a possibility that I'll mention at the end. G, where G is, get which one G was. I think it's that one, because there are two tidal filaments here, but there's no doubt about the origin of this. It's gravitational interactions between the galaxies. So that's a bit different from most of the others. No? This is part of the paper in which you published the big image of Stephan's quintet. They do some analysis of the quintet. And here's another pulsar image around the galaxies, in which you can see some more blue color in the galaxies, which are producing stars. Here and here, in the interaction, the red halo around the whole blue. These are the different parts: outer tail, inner tail. The outer tail is our G. H is the one that looks like an M, is a bit more convincing than some. It seems to follow some of the stars. So there's an idea here that this is sort of reflection nebulosity, like you have in the cluster the Pleiades, which does have diffuse light around it, as well as the bright stars, which can be just reflections of the light of the stars of dust grains in the area between them. So that's a possibility there. So there are still plenty of annoying bright stars in this field. Them in detail. I think yes, that ends the survey. What we can do quantitatively on this is a bit limited, because you can see what wave bands each emit in and deduce their nature from that. For distance, we don't have the distance, although for some of them we can say more probable galactic or extragalactic. What we have here is all the different distances and luminosities for a range of possible distances. As I said, we're looking out in a cone into space, effectively. So we could say, well, there aren't too many, from where the sun is in the Milky Way, there aren't too many big interstellar gas clouds for about 100 parsecs. We're in a sort of bubble, so 100 parsecs is probably the minimum distance, so 300 light years. DD is Disco Delgado. It's the thin disk, the edge of the disk of the Milky Way, because they're galactic, they're not really going to be further away than the edge of the disk. You can see from that different dimensions, it's about 10 times further away. That's about a kiloparsec. DG is Disco Grueso. We currently have two disks in the Milky Way. There's a less dense disk a bit further out, which takes us 3 times further, 3 kiloparsec. Or we could put them where the nearby galaxies are, the big one and the one in the quintet that's not part of the quintet. Or we could put them at the distance of Stephan's quintet, which is about 80 megaparsecs, a bit far. That's when we can get 5 galaxies in the field. So the possible dimension, we'll change these to parsecs now, but if they're close, they really only are less than a parsec. So they're not big filaments. They're not those big gas filaments that you read about sometimes in interstellar medium papers. They're fairly small things, so they could be cirrus. They're less than a parsec. At the edge of the disk, where we get to 5.9 parsecs, so at least they're not huge. If they're as far away as the galaxies, considering it's the same angle for all, of course, they get really big, 24 kiloparsecs for the nearby galaxies, 140 kiloparsecs for the faraway ones. And that's a bit far for a filament connecting galaxies. They can be half that. Yes, I'm not sure they could be that big. So the size itself does give us some limitation on the brightness. So if they're close, their total magnitude only sums up at 11, which is tiny. At the edge of the disk, they would be, well, it's absolute magnitude, not magnitude. Whereas if they're at the distance of the galaxies, they're the negative absolute magnitude. It's almost as bright as a galaxy, which is also the same in solar luminosity. Stephan's quintet was recently more famous for being one of the first 5 objects to be published by the James Webb Space Telescope. And if you haven't looked at that image, I recommend you do and magnify it, because it's interesting when you look at it, that you see that many of the little points are just galaxies and they're very far away, thin disks. I think you see on stars, most of those are different galaxies in the background. So it's worth getting it and magnifying it to see all the different parts, and it obviously reveals the increased resolution, much more structure in the combination of various wave bands again to get the to get the sort of more, as James Webb goes from visible into quite far into the infrared. So these are some of the areas of heated dust and gas in the infrared. One thing they couldn't get right is the orientation. You know, it's not in the same direction as the others. North will be north is sort of up here. So I don't know why. Not sure why it's quite wide there at an angle. But see the fine detail in that image. All the pretty pictures coming out seem to have Stephan Quintet, but they haven't done the filaments, fortunately. The last thing about Stephan's Quintet is the radio observations. The 500 meter aperture synthesis telescope in China, which is like Arecibo but twice as big. The big radio dish, as the big dishes themselves don't have the resolution. So the gas they've detected here is just a big, probably has more structure than this, but we just see a big source that wide because you need lots of dishes to get resolution, like the VLA in New Mexico. There's a huge halo of hydrogen gas centered on the Quintet with features more below than above, and below Stephan's Quintet none of the filaments are, so the radio doesn't seem to be associated with any filaments, so that probably reduces the extragalactic possibility. This is gas at the velocity of the Quintet. There's one other interesting observation that was, I'm not quite sure it's even been published yet, but this is gas around the nearby galaxy, 780 kilometers a second. It's the close galaxy in Stephan's Quintet. The one at the bottom, that has its gas emission as well, and it has a sort of finger. It's not really a finger, it is sort of a blob, protuberance pointing towards the other galaxy. The interesting thing in that is what else points towards the other galaxy? E and F. So we've been speculating whether these are connected. So these are to do with the galaxies up below, but actually, no, to do with that galaxy that's not part of the Quintet. There's also gas from the nearby galaxy, which is sort of reinventing the spirit of art. There's some connection between these galaxies. Or even that the redshifts are wrong, but that's a bit controversial. And that's one thing we do. We did try a proposal for the FAST telescope this year. The problem is it's sort of 6 times oversubscribed. So we get all the basically all of a support. Just very interesting reinterpretation of historical data. Does it say how galaxies form or anything for cosmology? No, right? No. It's difficult to get time unless you're investigating the beginnings of galaxies and the formation of the universe and all that sort of thing at times. So this is a bit of gas. Who knows where? Doesn't get the time. So we're going to have to look for smaller radio telescopes that are still working. Arecibo would be good, but it's not. It's closed. So, is there anything else to say here? I said yes. That's doubt for the future. Well, there are also the low surface brightness galaxies. As I say, I don't really work on those. Part of the data we had on the Virgo cluster with the 13 hours was shared with another group who were looking at the low surface brightness galaxies. So we didn't do that, they did. But first of all, I'm going to show you what one is. This is Malin 1. Malin was one of the pioneers of deep photography of galaxies with image enhancement as well. Is that the galaxy? That's only its bulge, that's only its center. The galaxy is all over here. Actually really big as well. See in the center, these are the faint arms, but they're mainly emitting in gas, not in gas and not in optical light. You know, basically, it never really formed any stars in a low surface brightness galaxy, so it's just about that. The disk is just about the limit of detection. And the only other things I've got here are that I hodgepodged this yesterday when for the battery of my computer ran out. These are some images from recent modular projects in the physics degree here, the Licenciatura, in which there's a couple of projects and people have been looking at galaxies which are elliptical or lenticular-like early type. And basically we're looking for unusual features. These are some more of the color maps which show relatively distribution of stars, whether they're more red or yellow. So we don't seem to reach blue in these. This one seems to have a sort of halo around it for some interaction, because the galaxy is there, but there's more light on the side, and sometimes they can be quite asymmetric. So we have to check out background problems for that sometimes. This one, well, it's been modular projects and undergraduate thesis now. This galaxy seems to have three parts, and using a two-dimensional fitting of the image, does three structures do work? It's usually when there's different color stars, they're part of different structures. Like this can be a little disk in the middle, which is more towards the blue. I mean, yellow being more blue than red. But there seems to be a reddish component around it there, but the rest seems a bit more an in-between color. It can be, not all the maps show it so clearly, but it is in this one. That one filter subtracting another logarithmically, so they're basically proportions of flux in red and blue. Well, although we can just change the scales, basically the calibration of the different colors in. But obviously we can flexibly change the appearance. That's why they don't always look very similar, because just choosing a different image. This galaxy seems to have different colored parts. And this can often be related with searching for data in different wave bands as well. This is R minus I, which seems to indicate 1 by 1 minute of arc is only the center of the galaxy. It seems to have a nuclear structure within it, more greeny blue for around a red spot. This is it in this is 8 microns. Near medium infrared is the source in the center. This is ionized gas from Sauron. What Sauron stood for. The idea of the eye that sees everything, and through seeing an instrument, which is what you might call it. I think that's the name. In which we can take different images at different velocities through the galaxy. You know? Integral field theory. I remember the name in a minute. Integral, but this is mapping ionized gas in the center as well. So there's quite a lot of different things happening in the galaxy. So main things, we can take some images from the optical, but we have all the different sources of data to compare with to see what's visible in the images. I think that's your lot. Yes, 1 hour. That was good timing. Thank you very much. I said it would have been slightly different if I'd actually had internet yesterday. What I did want to talk about a bit instead of some of the detail was our codes of stellar population synthesis. You know, we're basically all these different colors, all the different emissions, not only in the visible but in other bands. We can load all the spectral information there is, what lines there is, what temperature they're at. So what spectrum will be produced for stars of given type in a galaxy. We will then just have different proportions of stars of different types until we reproduce the colors of the galaxy or reproduce its spectra, the composition, and they're called stellar population synthesis codes for simulate that. I know there are some people who don't like us astronomers using big codes and not understanding how they work. But it's sort of a shoulders of giants thing, but the code gets written and people add things to it and correct it. In other words, it's always wrong, but it's always improving. It's always being updated, no? Which can mean you can do another paper later and you've got a better code. So but the idea is to simulate what we observe in that. So, and this basically, of course, does use all the quantum physics and statistical physics data that's available to calculate the probability of the line transition. Whether a given line is going to appear or not under the certain physical conditions that there are. No? So they really are very elaborate programs and improving all the time. And we use those to, even just with a 2-color image, we've got 2 bits of the spectrum. No? So we are predicting, R minus I, we are predicting the relative amount of light in the 2 bands, which It's part of predicting its spectrum. No? In astronomy, we can get a good spectrum from 2 points. But that gives you the gradient of the black body continuum. So even that works quite well. Some context. Okay, thank you very much. Bye.
Questions?
Questions, doubts?
Filaments life is long. The structure seems like not so. If they
How
have-
stable, you mean? How are they? In terms of observing them, suppose we only have a few dozen years for some of them to answer that. In interactions, well, in the gravitational interactions, yes, there are simulations for those, because for the interacting galaxies, we also have the n-body codes, which basically calculate the force between every pair of points, and which represent stars. Although for a galaxy of 10 to the 11 stars, at that moment the codes still only have about 10 to the 7 points before they, and that chugs away in a supercomputer for several weeks to get the simulation. No? But they do predict the forms, and in those, I think, the interaction time, the dynamical time of the interaction is about 10 to the 8 years as a minimum. No, 10 to the 9 probably to complete. What's that? 100 million years to complete the interaction, and the filaments are formed and decay in that time. No? At the end of 10 to the 9 years, you've probably got an elliptical galaxy formed without filaments, but maybe a bit before the end, you've got something like this, which is more material around it still before it falls back into the galaxy. So yeah, those filaments can last 10 to the 8, 10 to the 9 years. Cirrus clouds in the Milky Way, not so sure about those. They're quite small, if they are these. So I'm not sure what their lifetime would be really, because they depend on ionization processes. For example, the high temperature stars doing the ionizing, some of those only live 10 million years. That's more. The filament would still exist, but not be illuminated because not ionized.
If this is connected like between 2 galaxies, the filaments, then it's more stable.
Well, yes, they probably last longer if they are. Actually, it's a different direction. No, you don't see it. Well, there's one. That's all great. Yeah, a bit better. Yeah, so these are part of the interactions, and so probably are like that. So they can move out to the galaxy because they're originally in a circular, more or less, orbit. But the gravitational field is disturbed, but stars do go off together. So they're close enough to be bright enough to form a filament. And these interactions do take about 10 to the 8, 10 to the 9 years to complete. Yeah. Yes, these are once in one of the galaxies, and they'll probably fall back into one of the galaxies because they don't have what you call it, escape velocity probably in the system.
Questions?
Anything up there? No. Astronomy expert? No. Okay, well,
Thank you.
thank you very much. Do we have any online audience? No questions.
Questions?
Okay, it's not.
Usualmente las preguntas en YouTube suelen ser muy en diferido.